Great. So it's an honor to be here. And my plan for today is to talk about a recently very popular programming language concept called algebraic effect handlers. And I will start with an overview of what algebraic effects are, why they are useful, and how to use them. And then I will briefly talk about my recent effort to combine algebraic effect handlers with parallelizable computations. So let's get started. Since we are at Lambda days, I suppose we all love functional programming, where programs are easier to reason about. But in practice, we must also interact with the outside world. For example, if you want to do input and output from the command line, or if you want to read to and write from a file, or your program might throw an exception, or you might want to use some mutable resources in your program, or you might want some forms of concurrency and backtracking. So basically, effects are everywhere. But in many programming languages, those effects are often ad hoc and hard-coded, in the sense that each of the effects is implemented separately, and you cannot really change the behavior of those effects. So the question is, how can we support computational effects in a modular way? Well, the first thing that comes to mind might be monads. We will get back to this when we briefly compare algebraic effect handlers to monads and monad transformers. Instead, in this talk, I want to convince you that algebraic effects and effect handlers provide a composable and a structured abstraction control flow that allows us to define and use computational effects in a flexible way. And algebraic effects and effect handlers are a relatively new concept from the community, where algebraic operations are introduced by Plotkin and Power in 2003, where they established the categorical semantics foundation for algebraic operations, which, roughly speaking, are operations that satisfy certain algebraic laws. But while algebraic operations allow us to construct, combine, and reason about computational effects, they did not tell us how to handle effects. So later, handlers of algebraic operations are introduced by Plotkin and Pretina in 2009, which we can use to handle effects from a program. So in a sense, algebraic operations and effect handlers are the constructors and the destructors of computational effects. There has been a growing interest in algebraic effect handlers in academia. For example, this paper from PLDI 2021 discusses an implementation of effect handlers in the OCaml compiler, with the main motivation being to support asynchronous I/O in order to support highly scalable concurrent applications. And the implementation has been integrated into the OCaml compiler since OCaml 5. And at Uppsala 2022, this paper presents a high-level effect handlers library for C++, and the authors have presented lots of examples, including cooperative lightweight threads, generators, actors, and etc. More recently, from last year's Uppsala 2023, this paper discussed an implementation of effect handlers in order to support non-local control abstractions in WebAssembly. And they have presented a prototype implementation in Weizentheim. And it's not only about academia. There is also a growing interest in effect handlers in industry. For example, GitHub has this code analysis service called Semantics that uses effect handlers in their production. And React is a JavaScript library for building user interface by Meta, and they use effect handlers to design hooks that allow developers to reuse stateful logic. And lastly, Pyro is a Python library developed by Uber, and they use effect handlers for creating new inference algorithms for probabilistic programming. And the people at GitHub and a few others published a paper at ICFP 2022 where they discussed how they applied a variety of programming language ideas in the design of the semantics, the code analysis service. It's not only about algebraic effect handlers, as in this paper, they also discussed other programming language techniques, including generalized LR parsing, data type a la carte, and recursion schemes. Especially about algebraic effect and handlers, they have showed that using algebraic effect handlers, it's easy to handle an effect differently in different contexts. So these two paragraphs are taken from this paper, and I'm just going to read them for you. So an example of the utility and flexibility of algebraic effects is an effect we developed to extract telemetry data from our production Haskell systems. In a production context, we wanted this data to be uploaded to an aggregator. In a development context, we wanted to see them reported on the command line, and when running automated tests, we wanted to discard them entirely. And using algebraic effect handlers, you can easily handle the data emission effect differently depending on the context. So far, I hope I have convinced you that effect handlers are useful, but I haven't told you what algebraic effects handlers actually are. So let's look through algebraic effect and handlers through an example. So on the top of this slide, I have defined two effect signatures. First, I have defined an effect choose that comes with a single operation choose that takes a unit and returns a Boolean. And I have also defined another effect called exception, and it also has a single operation that takes a unit and returns a polymorphic variable. And with effect signatures, we can already start using effects operations in a program. For example, if we want to toss a coin, the program toss takes a unit, and then it performs the choose operation. And depends on the result. If it's true, then we are going to return heads, or otherwise we are going to return tails. And what's interesting is also in the type signature of toss. So the type signature of toss says that it's a function that takes a unit and returns some data type toss that has only heads and a tail. But more interestingly, this type annotation has an effect information that says it's a function that may perform effect from the choose effect. And also maybe a few others in this epsilon, but we don't care about the other effects now. We say that this program might perform the choose effect. And in this program, we can use a single operation, choose, in a program. But more generally, we can also use multiple effects in a single program. For example, if we want to toss a coin when you are drunk. If you are drunk, you may fail to toss the coin. So first, we are going to perform choose, and only if choose returns true, we are going to toss the coin. Or otherwise, we will return fail directly. So in this program, we are using the two operations choose and fail at the same time. So the effect signature of this drunk toss also says that now this function may perform two effects, choose and exception. And the relative order between these two effects do not matter, as we will talk about this briefly later. So with effect signatures, we can already start using effect operations in a program. But we don't know yet how to handle those effect operations. And the semantics of algebraic effect operations are given by effect handlers. So effect handlers, roughly speaking, defines what happens when an operation is performed. And in this case, maybe fail is an effect handler for the exception effect. So it defines what happens when fail is performed. And it also comes with a return clause that is applied when the computation does not perform an effect and just returns normally. In this case, maybe fail will, roughly speaking, turn the result type of this computation into a maybe data type. So if fail is performed in a program, then this fail operation clause is applied. And in this operation clause implementation, it is just a function that accepts two arguments, where x is the argument to the operation, in this case unit, because fail takes the unit. And more interestingly, it takes a second argument k, which is the continuation captured from where the operation is performed to where the handler is used to handle this operation. And in this case, maybe fail does not use the continuation. Instead, it just aborts the computation and it says, let's return nothing. And for the return clause, it says, if the computation returns normally, then let's wrap the computation result inside adjust. So I have some examples on the right of the slide. If we handle just the value 42 using the handler maybe fail, then we will get back just the 42 because this is where the return clause gets applied and we wrap the result inside the just. Or if we handle fail with maybe fail, then we will get back nothing. And this is what the operational semantics of the handler gives us. Maybe fail is a handler for exception. And similarly, we can also define a handler for the choose operation. The true choice is a handler for the choose operation that always returns true when you need to make a choice. So the choice implementation says that, again here, x is the argument to the operation, in this case a unit, and k is the continuation. And the choose operation in this case says that let's continue with the original computation with the choice of true. And in this case, the return clause does nothing, it's just an identity function. So if we handle 42 with true choice, then we just get 42 back because this is where we apply the identity function. But if we handle the toss program that we just saw from the previous slide that returns heads if the result of choose is true, otherwise return tail, in this case, we are going to return heads because the operation of choose inside the toss program will return true in this case. And more interestingly, because we have the continuation k available, a handler may choose to resume the original computation multiple times. So this all choices is, again, a handler for choose. But inside this choose operation, the handler says, let's resume the original computation twice by calling this k twice with true and false respectively, and concatenate their results. And in this case, the return clause wraps the computation result into a singleton list. So now, if we handle 42 using all choices, we will get a list back with only a single element 42. But if we handle toss with the handler all choices, then in this case, we are going to get a list with both heads and tails, because we resumed the computation twice with the choose operation returning true and false respectively. And from the example on these slides, we are handling just a single operation. But we also have an example where we have multiple effects in a single program, which is this drunk toss program. And to handle multiple effects in a program, we just need to apply multiple handlers. So in this case, we are handling this drunk toss first with maybe fail that turns the computation result into a maybe data type, and then with all choices that turns the computation result into a list. So in the end, we get a list of maybe. And in this case, we get a list of just the heads, just the tails, and nothing. Because if you reason about this program, the first choose operation from drunk toss is going to return true and false respectively. And in the first case, the second choose operation will also return true and false respectively. And the maybe fail will turn heads and tails into just the heads and just the tails. And when the first operation returns false, this fail will return nothing. And we just concatenate all results together, and we get a list of just heads, just the tails, and nothing. And more interestingly, with algebraic facts and handlers, is we can actually swap the order in which we apply the handlers. So instead of first handling the operation with maybe fail and then all choices, we can also handle the program with first all choices and then maybe fail. And in this case, we will turn the computation result into a maybe of a list. And in this case, we just get nothing because as long as a fail operation is performed from this program, this maybe fail handler will turn the whole computation result into nothing. But this example shows that we can compose effect handlers in a more modular way, and especially when we perform an operation from a program, we did not need to specify the order how these handlers are going to be applied. And instead, we can decide it later when we actually handle the program with handlers. So looking at those examples, now we can get a little bit more formal into the operational semantics of algebraic effect handlers. So first, don't get afraid because these 3 rules on this slide really summarizes what's going to happen with effect handlers. And let's go through these rules. So we have 3 rules. At this point, I haven't told you the syntax of this language, but the syntax of this language is really just the normal Lambda calculus, plus a handler expression that says we can handle expression using a handler H, and also an operation expression that can perform an operation by providing an argument. And we have 3 reduction rules. The first one is the normal beta reduction for Lambda calculus, where if we apply a function to a value v, then it's going to evaluate to the function bounded e with the variable x substituted by values. So it's call by value, although in this case, the fact call by value does not matter. And when we handle a program with a handler, there are basically 2 cases. First, a computation may perform no operations, and it just returns a computation result normally. So that corresponds to the second reduction rule, where we apply the return clause from the handler. So this reduction rule says, I'm currently handling a value v with the handler h, and I'm going to first get the return clause from the handler and apply this return clause f to the computation result v. If instead this program performs an operation, then the third reduction rules apply, and which says if you perform an operation, then I want to find the innermost corresponding handler to handle this operation. And we express the fact that we want the innermost handler for this operation by having this capital E, which stands for evaluation context. And the evaluation context is, roughly speaking, an expression with a hole. And it tells us where should we evaluate if we are inside a larger context. So the definition of the evaluation context says it is either a hole, or if it's an application, then we'll first look at the function position. If the function position is already a value, then we will look at the argument position, or we can look inside a handler. And the third reduction rule has the condition that this op is not handled by any handler from the evaluation context E by having this op not in BOP E notation. And in this case, this handler H should handle this operation. So we have the operation op maps to H inside this, map to F inside this H. And if we are going to handle this operation using this handler, then this expression is going to evaluate to the operation clause F applied to the operation argument V, as well as a function which we call the continuation. And the continuation, as you can see, captures from where this operation is performed to where this handler is used to handle this operation. And it's a function basically waiting for the result of the operation. And having the continuation available, it allows us to decide how we want to use the continuation inside this handler implementation F. So this summarizes the operational semantics of algebraic effect handlers. And I would also like to remark that this is what normally people call deep handlers in the literature. in the sense that the captured continuation also reinstores the same handler. This is useful, especially if, say, you have a list of operations, say, like get and set and set and get, and you want to make sure the same handler is used to handle those different operations. And there are also some variants studied in the literature. And one of them is called shallow handlers. And for shallow handlers, the captured continuation does not reinstore the same handler. And the people have shown that shallow handlers can be useful, especially if you have a producer and consumer pattern where you want to use the continuation as a computation that is waiting or is consuming the next resource. And there is also another variant called sheep handlers. So it's a combination of shallow and deep, so sheep. So sheep handlers is like shallow handlers. It does not reinstore the same handler. But it's also like deep handlers that it requires you to reinstall a handler for the same operation. So it may not be the same handler. I have not seen sheep handlers a lot in the literature, but it exists. And another thing I would like to remark on is sometimes you will also see people study a more generalized semantics of effect handlers that is called parameterized handlers. And for parameterized handlers, it's really that it's just the handler edge that can carry a state associated with the handler. So in this case, S is the value that is associated with this handler. And it evaluates to the operation clause F, now also takes the current state of this handler. And the continuation, the captured continuation now also takes a potentially updated state S prime that will be used when the continuation is resumed. And parameterized handlers are especially useful if you want to have some local stateful resources associated with the handler. And we will also be using parameterized handlers sometimes for examples in the rest of the talk. So that's about the operational semantics. Since we are in an effect system, we also want to make sure that all effects from a program are handled. So normally, people use an effect type system to keep track of the effect information of a program. So I'm not going into details, but in this particular case, you can notice that this judgment form says that under the typing context gamma, this expression E has some type A, and it may perform effect in this epsilon. And this typing rule for OP basically says that if the operation is an operation corresponding to the effect label L, then I must have L in this effect information. And handler basically eliminates an effect label from this effect information because in this case, this label L is handled by this handler. And I would also like to remark that in different languages or different papers, people have been keeping track of the effect information in different ways. So for example, in the research language F, people consider effects as sets. And the advantage is that you can use a notion of subset to easily use a program with less effect inside a context that has more effects. And more commonly, people also use row types to keep track of effect information. And with row types, people use row polymorphism to enable, to allow you to use a program with fewer effects in a context with more effects. And inside row types, we also distinguish between simple rows and scoped rows. And the particular two typing rules I have shown here correspond to scoped rows, where the main difference is in scoped rows, we allow duplicated labels, and that's useful when you have, for example, multiple handlers for the same effect in your program, and with extra language primitives, you can specify which handler you want to use to handle the operation. So it does not have to be the innermost one, but for example, the second innermost one. So having looked at the semantics and type systems of effect handlers, let's look at one more example, which is lightweight cooperative threads. And in this case, I'm defining an effect co-op that has two operations. So generally speaking, an effect can have as many effect operations as you want. In this case, yield is an effect operation that takes a unit and gives you back a unit. And fork is an operation that takes a computation that takes a unit and returns a unit, and fork itself also returns a unit. And with this effect signature, we can define a function scheduler that handles a unit-taking function f. So inside this function, we apply f to a unit, and we handle this whole computation using a handler for co-op. And here we assume we have some effect for q. So in q puts a function inside the q, and the dq gets the first available function from the q. And in this case, the handler says that if you yield, then I'm going to put the rest of the computation, in this case, just this k function, into the queue. And I'm going to get the next available function from the queue, and I'm going to run next. And if you want to fork a computation, then similarly, I also put the current continuation into the queue, and I'm going to invoke the function you are going to fork, and I'm going to make sure that I also handle this computation using scheduler. And the return clause applies when the current computation finishes. If the current computation finishes, then we are going to get the next available computation from the queue, and we are going to run the next available computation. So let's assume there is always a computation in the queue. And with this scheduler, we can write a program example like this. So in this case, we are going to print lots of letters, and we are going to fork and yield at different points of this program. And you can verify that all those letters are going to be printed in the alphabetic order. So basically, we are going to print A, B, C, D, E, F, G. And the reason is because when we fork, we will put the rest of the continuation in the queue, and when we yield, we will also get the next available computation from the queue, and so we mess with the evaluation order to make sure that all those letters are printed in this specific order. So to summarize algebraic effect handlers, as we have seen, algebraic effects can define a family of operations without specifying the semantics of operations. And those semantics of the operations are actually given by effect handlers that are defined separately. And we can very easily compose effects and handlers in a single program. And we can also handle effects from a program using effect handlers in different orders. And as I said, I will slightly go back to the point where we compare algebraic effects versus monads, and especially monad transformers. So there's a paper at Haskell Symposium 2019 that compares the relative expressiveness power of algebraic effect handlers and monad transformers. And the conclusion I learned from reading this paper is, roughly speaking, we can consider algebraic effect handlers to be more modular, especially if you have multiple effects in a single program. Where if you use monad transformers, for example, you will have to lift operations if you are using operation of an effect that is inside a monad transformer. While monad transformers can more easily express what they call scoped operations. So for scoped operations, you can consider, for example, if we have a transaction block and we can perform an exception inside this transaction block. And you want to say that if an exception is performed, then I want to roll back this whole transaction. So this exception is scoped over this transaction block. And those kind of scoped effects can be more easily expressed using monad transformers, while there is also an active line of research on how to support scoped effects using algebraic effect handlers. So this summarizes algebraic effect handlers. And in the next part, the second part of this talk, I want to talk about my recent work on a combination of algebraic effect handlers with parallelizable computations. So to demonstrate the issue we want to solve, let's consider another example. Let's say there is an effect signature that defines a writer effect that has a single operation accum that takes an integer and returns a unit. So the idea is that this accum will accumulate all the integers you passed to this operation. And we can define a handler for writer, basically using parameterized handlers because we want to keep track of the value we have been accumulating to using a stateful variable. And in this case, the handler for accum takes 3 arguments. S is the state that we have accumulated so far, and X is the operation argument, in this case, an integer, and K is, again, the continuation. And we will resume this continuation with an updated stateful resource, which is just the result of adding S and X. And then we are going to resume by also providing the unit as the operation result. And the return clause simply wraps the computational result together with the stateful resource inside a tuple. So with such an effect, we can write a program, for example, at the bottom of the slide, where we would like to accum 1 and then first accum 2, and we are going to handle this program using the handler haccum with the initial parameter of the handler being 0. And if we do that, then the result of this computation is a tuple with the computation result unit and the final state 3. And from this example, it may look like we have to run the effect operations sequentially because, well, they are writing to the same stateful resource. So the question we ask in this work is whether we will be able to run operations in parallel, and especially if we want to support user-defined parallelism behaviors. And well, as we have seen, one difficulty in doing that is, for example, in this case, these 2 operations are writing to the same stateful resource. And moreover, with effect handlers, the first operation, when we handle the first operation, the continuation will have available in its continuation the second operation. So the handler may or may not call the continuation to invoke the second operation, so it's difficult to predict whether or not we will be able to run the 2 operations in parallel. Well, since we are talking about parallelism, we first need to decide in which notion we want to write parallel computations. And in this work, we borrow the parallel computation notion from the paper on the DEX programming language, which is also a research programming language for array programming. And from this, from the notation from the DEX language, so they have introduced a notion of 4 expressions to express parallel computations. And the idea is that the 4 expression is going to construct an array by evaluating the body of the 4 in parallel. So it's a little bit different from 4 expressions in C or C++, because here it constructs an array. For example, here we have this inc function that takes an array. So the type signature for X says that it is an array that has n elements, and the element type is integer. So we have some form of dependent types to keep track of the length of an array on the type level. And inside the function, we are going to construct another array, which also has length n, and each of the element is the element from X plus 1. So if we apply inc to an array with 1, 2, 3, for example, we will get back another array with 2, 3, 4. And more interestingly, DEX also supports some form of accumulative effects inside the 4 expression. So for example, we can write the program sum that sums an array. And in this case, we are also taking an array of length n with elements integer, and we are going to use this runAccum function. And for this runAccum function, y is the accumulative variable that we are writing to. And inside the body, we have this 4 expression, And each element of this for expression basically adds the corresponding element from x to y. So if, and because run-accum returns a tuple of the computational result, in this case just an array of units, and then the final state, we use the second to project out the final state of y. So if we apply sum to an array of 1, 2, 3, then we will get back 6. So at this point, we can see that DEX does support some form of effects inside for expressions. But actually, run-accum is the only effect that is supported inside for expressions in DEX. So a natural question then is, how can we support more parallel effects or more effect operations inside parallel computations if we express parallel computations using for expressions? And before I talk about our approach for parallel algebraic effect handlers, I want to make a brief stop and talk about what kind of properties we want from a system that supports algebraic effect handlers and parallel computations. We want this system to be extensible, so users should be able to extend the system with new effects. And we also want to support user-provided parallel semantics, just like we want to support user-provided semantics to effects. And just like we want multiple effects in a single program, we also want multiple parallel effects in a single program. So sorry about this 3850. I'm trying to keep track of time on my slides. To design a system with those properties, our key design is we have a system that has both effect handlers and those for expressions, and we interpret for as an effect. If we interpret for as an effect, then we are able to write a program like the one at the bottom of the slide, where we have a for expression under a handler, and inside this for expression, we are going to call the accum operation. And after we are done with this for expression, we just return the string down. And we can handle this whole program using the handler for run accum with the initial handler parameter being 0. So what happens if we write a program like this in our system? Well, we need to, since we said that we interpret for as an effect, now a handler is also responsible for handling this for as an effect. So now each handler has to implement a traverse clause that handles for expressions. And in the traverse clause, in this case, it takes 4 arguments, where n is the length of the iteration, so the length of the iteration of the for expression, and s is the current parameter of the handler, and l is something special that we'll talk about, what we call body continuation, that is, roughly speaking, the body of the for expression, and k is the normal continuation that waits for the result of the for expression and resumes the original computation. So to demonstrate how this accumulative handler is actually applied to handle this previous computation, let's go through the evaluation derivation of this program step by step. So first, if we are going to handle a for expression using a handler, now what we are going to do is we are going to get the traverse clause from the handler. In this case, we are just going to name it traverse haccum, and we provide 4 arguments. First, the length of the for expression, in this case 3, and the initial handler parameter, in this case 0, and an array of body continuation. And each of the body continuation really is just the body of this for expression, except that we now also push the handler to be inside this for expression, so that if we push more and more handlers inside this body continuation, in the end we will get a pure body of the for expression. And then k is just the normal handler that waits, normal continuation that waits for the potentially updated handler parameter and the results of the for expression. And in this case, it just returns down. And this is the definition of traverse we have seen. So if we are going to handle this program using this traverse clause, then according to this definition, what we are going to do first is we are going to call each of the body continuation inside another for expression. But fortunately, in this case, the body of the for continuation is pure, because the effect inside this body continuation has already been handled by the handler we pushed inside this the body of the for. And we are going to run each of the body continuation using the initial handler parameter 0. So once we are done with calling the body continuation, we will get back a list of results, and each result is a tuple of unit, which is a computation result, and then the final state. And in this case, is 1, 2, 3, respectively. And then we are going to do some unzipping to get out an array of computation results and an array of stateful results. And we do some reduction to reduce the results of the final states. And finally, we will resume the original computation with the new state now being 6, and the final result, which is just a string of done. And the final result of the whole computation now is just the tuple of the result done and the final state 6. So this example demonstrates how we support parallel computations in the presence of algebraic effect handlers by asking the user to implement an extra traverse clause of effect handlers that are used to handle for expressions as we interpret for as an effect. And the updated operational semantics will make it a little bit more formal about what body continuations are and what continuations are. So in this case, so the first 3 rules are the same rules we had before, and the 4th rule is the only new rule that we added to the system to support parallel effect handlers inside parallel computations inside effect handlers. And in this case, it says that if you have a for expression with index I and length n and the body e, we are going to handle this for expression using the innermost handler, in this case, h. And in our system, every handler has to handle the traverse clause. So in this case, h is the innermost handler. This is expressed by the fact that we use the pure evaluation context f instead of the evaluation context e. And we don't have the condition that op is not handled by the b-op of the evaluation context, because it's always the innermost handler. And we use the innermost handler to handle this for expression by getting out the traverse clause from this handler, in this case f. And we apply it to the length of the for expression, in this case n, and an array of the body continuation. So in this case, we are modeling the unparameterized handlers. So each of the body continuation is just the body of the for expression, in this case e, with the handler h pushed inside this body, and it's a unit-taking computation, because we still want to make sure that the handler has full control over whether or not each of the body continuation should be called. And the continuation, the last argument to f, is just the normal continuation if you interpret for as an effect. So it is a computation that waits for the result of the for expression, and it resumes the original computation, again with the same handler installed. And with these semantics, we can already support the example of accumulative writers. And we have more examples that we probably don't have time to go through, but there are more examples where parallelism will make sense in the presence of effects. And one of the examples is weak exceptions. For example, if we want to run a list of computations in parallel, and each of them may throw an exception, and you would say, I'm going to evaluate all of them anyway, and after all of them finishes, I'm going to check whether one of them has thrown an exception, and if so, I will, in this case, return nothing for the whole computation, or otherwise, I can resume the original computation with all the results you got from running all the computations. And just like you can compose multiple effects in effect handlers, you can also compose multiple effects for parallel effect handlers. For example, if you want to run a parallel computation where each of the computation is accumulating some state and also some of them is throwing exception. And you can handle the computation using multiple parallel effect handlers, and you will get the result as is expected. In this case, nothing as the computation result because you performed an exception, and then you also get the final result that you have accumulated. So we have also provided a Haskell implementation for parallel effect handlers. And we also used a runtime tracing system that visualizes how each of the computation is actually used. So to make sure you can have a better understanding of when the for expression is evaluated in parallel and when the computation result gets back and how we resume the original computation. And there are lots of details I did not cover in this talk that you can find from this paper. So this paper is currently still under review, but we hope to put it up sometime soon. And in this paper, you will find more examples. For example, we also support non-determinism for parallel effect handlers, and we can do pseudo-random number generation, and also you can even have shared state among parallel computations. And we also talk about a type system for the parallel effect handlers with proven type safety. There is also a challenge in designing this type system because when you push the handler to be inside the body of the for expression, you did not know what type of the for expression would have. So we designed the type system in a way that is polymorphic over the computation type. So that summarizes the talk. So the main takeaways are that algebraic effect handlers by themselves already provide composable and structured control flow abstraction. And we are currently studying a new combination of effect handlers with parallel computations. And there is a list of resources that I would recommend. The first one is the effect bibliography that has lots of resources, like papers, tutorials about effect handlers. And there is also a tutorial paper, Introduction to Algebraic Effects and Handlers. And Sam Lindley has given a lecture on effect handler-oriented programming at OPLSS, and all the lecture notes and videos are available. And Dan Lehan and myself gave a tutorial at SFP 2021 about effect handlers, but more generally about the research language Coca that has built-in support for algebraic effect handlers. And finally, if you are wondering what does algebraic mean in the name algebraic effects, I would recommend the paper What's Algebraic about algebraic effects and handlers, but it will require some of category theory background. So that's it. I'm happy to take questions.